So my name is Michael Gurnis, and I'm speaking to you on behalf of the entire GPlates team. And the title of my talk is GPlates Cyber Infrastructure for Plate-Tectonic Reconstructions and 4D Dynamic Earth Models. The GPlates, which is the name of our software and software system, is an informal but now rather extensive international, I'm not sure what word to use, a consortium perhaps, and it's led at the University of Sydney by the research group of Dietmar Müller, and with substantial involvement by myself at Caltech, as well as with Trond Torsvik in Norway. Essentially, just a little bit of history of GPlates is that we essentially have developed from the ground up a piece of modern software which does plate tectonic reconstructions. And essentially we did this because all of the existing tools that existed within this very important area of the earth sciences essentially were either out of date or were entirely proprietary. So there was the need for essentially a brand new piece of software which was open source. So in addition to the main international partners who drive GPlates within the United States, I'm the only U.S. participant, is that we have heavy involvement with the EarthCube project, which I think that your RCN is deeply involved with, including and primarily an EarthCube building blocks program, which essentially is delivering web services in a common format. I'll talk a little bit about that near the end of my talk. And in a very teeny presence within a new small project called Geodata Spaces out of the University of Chicago, and our involvement there is to link geodynamic models up, including plate tectonic reconstructions. And you'll see, in addition, the work that we've done with Shannon Peters at the University of Wisconsin with MacroStrat and the Paleobiology database. So the outline of my talk today is just to give you a quick overview of the software and what it does, but give you a bigger picture on what the science driver are for, especially for myself, as well as some of the other participants within the GPlates program, to talk about what we call the GPlates Client. Okay, that's essentially what GPlates originally was several years ago, was a client, essentially an interactive program, and it allowed people to build plate tectonic reconstructions as well as geodynamic models. And I'll show you the client itself, and we'll talk a little bit about those reconstructions, both traditional reconstructions with rigid plate tectonics as well as with deforming plates. And then I'm going to describe to you some of the newer areas that we're heavily involved with in terms of both web services as well as an underlying Python framework to do the reconstructions and to drive the web services. So just a quick sort of overview of GPlates, mostly the client, but also the bigger workflow that we're involved with, is essentially software for interactive visualization, manipulation, and analysis of plate tectonics and paleogeography. So essentially, we can create, out of scratch, plate tectonic reconstructions or work with and manipulate existing reconstructions. We can visualize geospatial data through geological time. It's extremely important for individuals in a variety of different disciplines. Just more detailed, we can build detailed reconstructions from imported data, essentially work with raster data, line data, polygonal data, shape files, and you'll see these in more detail. And some of these things are actually linked to other kinds of Earth models, and I'll describe some of those models to you. So here's one of the big science drivers especially for myself, one of the things that we're interested in is thinking about the whole Earth as well as the whole Earth as a function of geological time. In some sense, you could imagine what we're attempting to do with these 4D dynamic Earth models is provide the framework and the context that GCM models or general circulation models have within the atmospheric sciences. Within the earth sciences, well, we don't have such a coherent, uniform way of doing that, especially on a global scale. And in some sense, that's what these 4D dynamic Earth models are. But in order to steer them, to steer data in them, and to bring data out of them for comparison with a variety of different data sets, one needs a context in which to describe the outer surface of the Earth. And of course, the outer surface of the Earth on million-year timescales is ever-changing. It's not a static perspective. The plates are moving, etc. And so this is just an example of a three-dimensional dynamic Earth model looking at the interior of the Earth. Now, for those who are more interested in the geological expression of dynamic Earth models, one of the things that we're heavily involved with and one of the big motivations for GPlates right from the start of the program a decade ago was really to organize, interpret, and to model the stratigraphic record on a global scale much better and to understand both sea level and basin structure. It's just one of the main topics that I'm interested in. And these are just examples of simulations in which GPlates played a major role in building the models and interpreting the models themselves. So the first thing I'm going to describe to you and show you, I'm going to bring it up, is the client itself. That's what we started with. We built a client from ground up using modern software tools, and one of the most important things for users as opposed to developers or for people who want to get underneath the hood is the fact that this is a cross-platform and it works on both Macs, Windows, and Linux. And we use a variety of open source software and tools, and the underlying software is primarily written in C++. And you can get the latest version of the software. The latest version is now 1.4, and you can get it from SourceForge by following GPlates, www.gplates.org, or just go to SourceForge, and you can get your own version of it. It's entirely free. At this point here, what I want to do is just to quickly move over to the latest version of the GPlates client itself, okay? So you're seeing my entire desktop here, and I'm going to come over to GPlates. This is GPlates 1.4, okay? This is version 1.4 that you can get off of SourceForge right now. And what I've done here is I've already loaded in the what we now consider to be the standard baseline reconstruction that is distributed. That was built by Maria Seaton at the University of Sydney. And so here's the primary window in the middle of my desktop, and you see a globe of the Earth there with a typical view of the coastlines today and an orthographic projection and a lot of different icons off to the side. I won't go into the details at all in here, but the first thing I wanted to show you and to describe to you is that at a base level, GPlates itself provides functionality which plate-tectonic reconstruction software has provided for many decades. That is, to take line features like we see on the surface of the Earth today, and maybe let's just reconstruct them back there into the Cretaceous, and we can just now move these features around, we can animate them, and essentially what's happening is that on the fly is that all of the line data that's loaded into the software, as indicated by the present-day coastlines, is reconstructed into its paleo positions. Now, one of the things that GPlates did, which was quite different from previous plate-tectonic models, is, let's say if you come over here to the Pacific, into the Pacific Basin itself, you know, there's just there's a void. You don't see any plate boundaries. You don't see anything moving around. And so basically often there was lots of open spaces in plate-tectonic reconstructions. And so one of the important innovations that GPlates introduced was the development of essentially a topological system in which the entire surface of the Earth at any moment of time could be covered. And so what we can do here is to bring up, for example, our standard topological model. And this essentially just allows you to show all the plate boundaries and all of the plates and entirely closed. Now, of course, for those of you who are familiar with geological history and plate tectonics, you realize that a lot of these plates have been subducted, and so this, in fact, is a model. But nevertheless, it's very important to build models such as this, such that they can be connected up with the mechanical models of the Earth, the 4D Earth models on the one hand, and those models themselves allow one to, for example, test those models by looking at seismic images inside of the Earth, because inside of the Earth's interior, as well known, as well established these days, is that we can see the relics of that subduction into the interior of the Earth. So another thing that you may have noticed is that this whole panel over here came up at one point. And this essentially is just layering, just like in programs like Photoshop or even in GIS software, you can actually have lots of different layers and whatnot. Now, one thing I'm going to do, and I've already brought this up, I've loaded the software in already, is that we'll look at raster images themselves. We're going to actually look at the topography of the Earth itself. And let me actually just zoom in on, let's say, the Atlantic Ocean here, and let me get rid of some of these topologies. Now, one of the things that many animations that you would have seen on the web and that different vendors actually provide is that they provide sort of nice, smoothly evolving animations of the continents moving. And they usually just use graphical morphing software to do that. Underlying GPlates, however, is a very intimate knowledge of the details of both plate tectonics as well as the age distribution in the ocean basin themselves. And that allows us to use rigorously the principles of plate tectonics to smoothly and continuously reconstruct, as we're watching here now. We're watching the ocean basin actually opened up. And so all of this new raster image, which mostly comes from the gravity field, is unfolded, and it does so in a continuous and smooth way. And so that's a very important innovation that GPlates has. And there's a number of different data sets underneath and behind the hood that allow one to do this. Now, what I'm going to do is I'm going to quickly switch, and I'm going to show you, to give you an illustration of some of the powers of GPlates themselves. I'm going to give you, go back to my presentation and show you how we brought a number of different pieces of data together in a particular reconstruction. Now, one of the innovations which GPlates has introduced on a global scale and merged with this interactive program is not just rigid plate tectonics, but deforming plates as well. Regional models of plate deformation have been an important component of earth science research now for about 20 years, and different research groups have developed regional reconstructions, mostly essentially independent of plate tectonic reconstructions. The version of GPlates that we now use, it's actually not publicly, this one is actually not publicly available, but it soon will, is the fact that the Earth's surface is either covered by rigid plates or deforming plates. And that allows us to reconstruct, for example, areas of extensive deformation, such as western United States. And so what we're going to do is we're going to look at an example in which we use data and introduced it into GPlates in a number of different ways. Okay? So for example, this is an example of data synthesis for North America. And what we would have brought in as a beginning piece of data is global plate polygons deforming regions, paleo age grids, and what's called a plate rotation model. Now, one thing we could do is let's say we could go off on the web and we could retrieve a bunch of volcanic rocks, their ages and composition. We could, let's say, retrieve these, as we've done in this example, with NavDat. And we could then get these as a normal GIS shapefiles. We could then have that on our system and then reprocess that data within GPlates to find out which plate-tectonic plate that they reside on. But in addition to that, this example also recovers data in a different way. GPlates, the one I'm showing you here, is a client, but it can go off on a web and it can access web services itself. And this particular example goes off and it retrieves data from a web service that's provided by MacroStrat at the University of Wisconsin. And we grab that data in real time with GPlates. I'm going to just show you a movie for the sake of time, but we go off and we grab that data. And then in addition to that, we could, let's say, go off and retrieve data from the paleobiology database. And so in some sense, GPlates in this example is almost being used, for example, like you would use, let's say, Google Earth, right? Okay, it's an application on your desktop, and you went off and you recovered data on the web. So here's just a couple of slides showing you standard coastlines in the present day. We go off and we make a polygon. We recover data over the web. We grab that data. It gets brought onto the system, and you can sort of see it's all color-coded differently because initially when it comes back on, it doesn't know which tectonic plate it's on. We need to assign plate IDs. There's an outline of a polygon. We assign plate IDs, and then we bring all of that data together. I'm going to show you all of that data now brought together, and it's on an animation here. And so now we go back. Whoops. This is hold it here. I need to go back to the beginning of this movie here. I think it's 140 million years ago. Nope, 100 million years ago. And so what we see here before it actually animates, you'll see all of the smoothly evolving boundaries between all of the plates. And this exists globally. Stratigraphically, what we've done is, not stratigraphically, but we've taken the sedimentary rocks and we've color-coded them by their type. For example, in red are marine rocks, and here different terrestrial rocks are in brown. Several other things will happen in this picture. One of the most important things is that when we get near the present day in the western United States, the rules of plate tectonics, of course, break down because it's a deforming plate. And you'll see the plate deforming, and you'll also see strain indicators for the deforming western United States. So GPlates is the only global model that allows one to do that in deforming regions. Well, GPlates is the only open source software in this field anyway. So anyways, here's the deforming region, and then all of these strain markers open up as the western United States opens up. Now, GPlates has functionality such that it can take all data existing in the present-day coordinate system and then use those deforming regions to make these reconstructions backwards in time.
Mike, you have about 2 minutes left.
Okay, so the next thing I really want to show very quickly is the fact that GPlates, not only can it access features over the web, but it can also be used as a web service itself. So underneath the hood, on our websites at Caltech, we actually have this. It's a service, and you can actually send data to it, and it will send reconstructions back. And so the group at the University of Wisconsin, this is their website right in here. I'm going to go to their website really quickly. Their website actually uses our web service. So theirs uses a lot of functionality, and essentially this is called the Paleobiology Database Navigator. Okay? And what you can do is you can just click on this icon right here where you see Africa and South America together, and you can just go back to a particular point on the geological time scale. Now, most of this has been run so many times, all of this data is essentially cached, but essentially you can just go to any geological time and it goes in to, you hit a time there, and then you can hit this reconstruction. And then here's the GPlates icon. It goes off to, originally it went off to our website. It did the reconstruction and it put it back. And so this is where some of the development activities for GPlates is now residing in, is essentially the ability to do these kinds of features. And so a lot of the development is in the web services, in deforming plates, and as well as essentially making the GPlates functionality available essentially through a Python API. And we're essentially using that for our web services. So that's some of the developments. And so hopefully that you found this information relevant, and if you guys have any questions, you can send me email, and if I can't answer them, I can send them off to any of the other many GPlates people around the world. So thank you.
Thank you, Mike.
You're welcome.
So we'll just wait a minute or so and see if anybody is typing into the chat window as we speak. Okay, here's a question. For those with deep time related data, what are the best ways that GPlates might make use of or access that data? I noticed a lot of use of WFS and shapefiles. Is that the best manner to deliver such paleo-related data? What about GeoJSON or other approaches?
Yeah, so I believe that we can handle shapefiles over the web. Essentially, our web service is processing GeoJSON data. So essentially, GPlates can handle all kinds of different data, even either the client, and hopefully in the future our web service will as well. So we can just take raw point data, and we have scripts that convert them from that raw data into what we call GPML, the GPlates markup language, which is a specific articulation of GeoSciML and GML. Or we can, there's functionality directly is to just read in different formats directly into GPlates itself. Of course, we can also bring in raster data as well. But yeah, I mean, hopefully we're using most of the formats that people would actually have, shapefiles or ASCII data, which we can convert into GPML. I can come over here if there are any more questions or not. For example, I can come over here to this window right in here. We can open various files. And here's, you can just see, here's various kinds of examples: shapefiles, raster, OGR, GMT files. There's different kinds of, even GeoSciML files we can bring in. This is also backward compatible. For many, many, many years, there was this program called Plates at the University of Texas, and it used a format called the Plates format, and many other plate-tectonic software that's mostly proprietary uses format, and you can use those, bring those in as well.
Okay, we have another question here. Mike, can you mention some of the efforts to compute physical paleooceanography in the GPlates framework, like sea surface temperatures and wind patterns?
Yes. So what GPlates does, of course, it can give you a picture of the Earth in paleo time. And so one of the things that that we have, for example, Maria Seaton at the University of Sydney does it. She produces paleo-age grids, and from those paleo-age grids, one can produce a paleobathymetry. And then with our other geodynamic models, we produce topography. So essentially, our models now are producing models of Earth topography as a function of geological time, from the Cretaceous to the present. And so Matt Huber, who's now at the University of of New Hampshire. He's a big GPlates user, and he makes his own reconstructions with GPlates. And he's actually a GCM modeler. So what he does is he builds models with GPlates, and then he incorporates that data into his GCM, and then he runs both ocean circulation and atmospheric circulation models in the past, and in those models he produces wind patterns and sea surface temperatures, etc. And I can provide details if the person wants to send me an email.
Okay, great. I don't see any more questions coming in at the moment. So thank you to both of our speakers today.
You're welcome.
Just to remind everyone, this webinar will be available later, both at the EarthCube website and the C4P YouTube channel, Cyber4Paleo. For future webinars, please check the C4P webinar schedule at the earthcube.org site. Thank you all for attending.